All right, class. Welcome to this video. It's taking me a little while to remember how to do this, but here we go. So a few things. Remember, exam 3 is a week from Wednesday, and we have a quiz tomorrow on Wednesday, and that quiz covers all the previous chapter. So really focusing on solubility with and without common ion, with complex ions, and with some of the titration calculations. All right, so let's get on to this. Let's go ahead and talk about the surroundings. What's going on where we have surroundings in the system, and we're talking about the entropy. Remember that the increase in the entropy of the universe, right? The entropy of the universe is going to be increasing all the time. That's the second law of thermodynamics. So when we were talking about water freezing last time, remember if water's freezing, the system here is water. Right? When you freeze water, you're going from a liquid to a solid. So when you're doing that, the entropy of the system, the water is decreasing. How is it possible that the entropy of the water can be decreasing? It's possible if the entropy of the surroundings increases. All right, so you can have a system with a decrease in entropy, and as long as the surroundings, the increased entropy of the surroundings makes up for that, so that the universe has an increase in entropy, the process will be spontaneous. All right. So let's graph what happens when water freezes. So remember, water freezing, this has a delta S that's negative, right? So it's not a favorable change in entropy, but it does have a negative delta H. It's exothermic, right? So that's favorable. And remember that the change in entropy of the universe is equal to the change in entropy of the system plus the change in entropy of the surroundings. And all of this has to be greater than 0 for it to be spontaneous. It has to be greater than 0. All right. So let's graph what this kind of looks like. This is kind of a strange graph, but stick with me here. So when is this favorable? So we think about it at low temperatures, right? At lower temperatures, things convert from liquids to solids. So what's happening? If we plot the entropy change of each of these, right? The entropy of the system, is negative, becoming more ordered. But at low temperatures, the change in entropy of the surroundings is greater. So what happens here is that at low temperatures, right, this is an exothermic reaction. That means it's releasing heat, right? So the surroundings absorb the heat that's released from water freezing. So that gives you an increase in the entropy of the surroundings. So when you add these two together, delta S of the universe is positive. But as you go to, and think about this, when you have a refrigerator, in the back of the refrigerator, warm air is coming out. What's happening, right? You're freezing stuff in the freezer, right? So heat is being transferred out from the freezer to cool things down, and that is done by compressing a refrigerant. And then what happens, the heat basically transfers from inside the freezer to outside of the back of your refrigerator. So you have the hot air coming out. That hot air is increasing the entropy of the surroundings. If you were to compare this to what happens as you go to higher temperatures, it's not spontaneous, right? So we still have our delta S of the system. That's the same. But our delta S of the surroundings is smaller because at higher temperature, there's already a higher entropy. And when you put these together at higher temperatures, this has a negative delta S of the universe, so that the spontaneity of this happening, this will be non-spontaneous at higher temperatures, and this will be spontaneous at lower temperatures. So as the temperature changes, it goes from spontaneous to not spontaneous, right? And at the point where that happens is the freezing point. All right. So how do we calculate the entropy change during a state change? All right, and so you want to memorize this equation. The delta S of the system here is equal to the Q reversible. The Q, this is the heat involved with the phase change. Remember, we talked about how to calculate that heat when we were in the last chapter of the last semester. And it depends on the temperature, right? So the temperature is important here, right? What are the units for entropy? Right, you get Q is joules, and temperature is in Kelvin, so the units are joules per Kelvin. So this is a relatively straightforward equation. You can calculate the entropy change of the system by looking at the amount of heat involved in the phase change. So this is for phase changes, and dividing it by the temperature. It has to be in Kelvin. So try example 19.2 in your book to see how that goes. All right, how do we calculate the entropy change of the surroundings? Again, another equation you want to memorize, the delta S of the surroundings. Now there's a negative sign. Let's go back. It's positive there. Here it's negative. So now it's the negative of the delta H of system. So this is for something that's at constant temperature and pressure. Negative delta H of the system, that could be the delta H for a phase change. It could be the delta H for a reaction. So it's the negative delta H of the system divided by the temperature. Right, so again, the units here will typically be joules per Kelvin. Right, you typically are starting out with kilojoules here, so you have to go from kilojoules to joules. So exothermic processes are going to tend to be spontaneous at lower temperatures, right? Because they increase the heat of the surroundings. If you have a positive delta H, then you end up with a decrease in energy of the surroundings. So it matters whether something is endothermic or exothermic. But again, another relatively straightforward equation. Remember now, for the surroundings, there's a negative in front of that Q. So let's do an example with this. We're given a combustion of propane. You know, if you're using propane or propane accessories, like King of the Hill, how does this work? Right, what do we have? We're given a delta H. We have a temperature. All right, again, this is going to become 298 Kelvin. You need to be in Kelvin. And so if you have this reaction, 1 mole of propane reacting, delta S of the surroundings is equal to minus delta H of the system divided by the temperature. And this was just one where you just kind of plug and chug through it. This is minus, but this is minus. So minus 2044 kilojoules over 298 Kelvin. This equals to, well, let's do it down here, 6.86. Now this is kilojoules per Kelvin. And typically when we're talking about entropy, we'll convert this. This is 6,860 joules per Kelvin. And that would be your answer. So again, this is what example I was saying, like when you're looking at this is a relatively straightforward equation compared to like the acid and base stuff where you're like, oh, is this an acid? It's just a base. It's just, you know the equation. You got to watch the signs. It's the biggest mistake you can make here, and the temperature. Make sure it's in Kelvin. All right. Let's talk about proteins. Where is this something that you might think about? Proteins, right? Protein folding is an extremely complex process. It's very fast, though. You take proteins, some of these proteins are extremely large, but they fold into their correct shape very quickly. When a protein folds, what do you think happens to the entropy of the system, the protein itself? Think about that for a second. You think it increases or decreases? You can pause this if you want to think about it. All right. So you go from a very disordered, long, floppy, basically like a long string that can flop around, has a lot of degrees of freedom. A lot of ways you can move it. and arrange it. But then you go to one very specific structure with very little, with a greatly reduced flexibility. So this would definitely be a decrease in entropy. So when you fold a protein, which all proteins fold to get to their actual state, you have a decrease in entropy. Okay. How is this possible? How is it spontaneous? You increase the entropy of the surroundings. Okay, you increase the entropy of the surroundings because look at all those water molecules that are around the string, all these little dots down here around the protein. There's a lot of hydrogen bonding functionality. There's the amine functionality. There's the carboxylic acid. There's a lot of polar groups that waters can interact with different intermolecular forces that are able to associate with that string. That means those waters have an order to them because they're not just any random place. When you fold a protein, they all get excluded because proteins don't tend to have very much water trapped inside of them. So all the proteins that were associated with, all the waters that were associated with the protein are now free. And so you increase the entropy of the surroundings that way. All right. All right, let's do another clicker type question. When a liquid evaporates, what is true about the signs of the enthalpy and entropy changes? So I'll go ahead and pause it if you want to think about it a second, and I'll give you the answer. All right. The answer here is A. Liquid evaporates. Well, evaporation is going from a liquid to a gas, right? And remember, as you're going from a solid to liquid to gas, as you go this direction, delta H, right? This is going to be endothermic. Delta S will increase. So it costs you energy to go solid, liquid to gas, but it's favorable from an entropy standpoint. When you're going the other direction, it's exothermic, and it's not favorable in terms of entropy. All right. Well, let's kind of quickly review what we've talked about so far in this chapter. All right, what is the equation that relates the delta S of the surroundings to delta H of the system? All right, so you want to know this equation. Now, if we combine this with the equation for the entropy of the universe, remember that's this equation, right? That the delta S of the universe is equal to delta S of the system plus delta S of the surroundings. What do we get? We get an equation for free energy, which you're probably familiar with. And we have the system there, but in general, we'll just write this as delta G equals delta H minus T delta S. This is the equation for what we call the Gibbs free energy, or you can just call it the free energy. What is the free energy? Okay, it is a thermodynamic potential that calculates the maximum reversible work that may be performed by a system at constant temperature and pressure. What does that mean? It means it's the energy that's free to do work. Okay, so it's the amount of energy. If you have a process, if you're an engineer, you have a process, you need to do something with that energy to do some work. The delta G tells you how much energy you have to do work. That's all. So for the energy that's free to do work. So for example, look at this reaction. Is that a spontaneous reaction? Yes, it has a decrease in delta G. What about this one? No, right? That is not spontaneous. So delta G, when negative, is spontaneous. There we go. Delta G negative is spontaneous. Delta G positive is not spontaneous. All right, let's look at a few calculations. Let's consider the reaction. 2 oxygen atoms in the gas phase goes to O2 in the gas phase. What's going to be the sign of delta H and delta S? And then would that reaction be more spontaneous at high or low temperature? So you might want to pause it while you think about it, but I'll give you the answers in just a second. All right, so what are we doing here? We're taking 2 atoms and we're forming a bond. So this will have a negative delta H because you're forming a chemical bond. You're forming a more stable situation. The opposite, if you're breaking a bond, they go to the atoms, that's going to cost you energy. So in general, if you're making a bond, It's going to be negative exothermic, positive to just break the bond. Now delta S, well, it's decreasing. So it's negative. Delta S is negative because you're taking two atoms that can be in the gas phase and can be in different places, and you're tying them together. You're reducing the number of degrees of freedom. So this has a negative delta H, exothermic, and a negative delta S. It's not favorable because you're reducing the entropy. So would this reaction be more spontaneous at high or lower temperatures? And it'd be at lower temperatures. What do we mean by that? All right, let's go and look. What do we mean by spontaneous at high or low temperatures? Let's look at this equation, right? We have delta G is equal to delta H minus T delta S. And so for something to be spontaneous, delta G needs to be negative. So let's draw a box. And let's make some squares in here. And let's look at how we compare it. We'll have delta H on the top. This will be negative and positive. Have delta S on the side. This will be positive and negative. So if delta H is negative is favorable, right? If delta H is negative, delta G, if you ignore delta S, if delta H is negative, delta G would be negative. Now, delta S, we want a positive delta S, because if we ignore delta H, that negative T delta S means that a positive delta S would give us a negative delta G. So things that have a negative delta H and a positive delta S will be spontaneous at all temperatures. It doesn't matter what the temperature is, delta G will be negative. All right, now let's look at the opposite case. If delta H is positive, that ignoring delta S would tend to give you positive delta G. Negative delta S is also going to give you a positive delta G. So things that have a positive delta H and a negative delta S will be non-spontaneous at all temperatures. Because at all temperatures, no matter if those are the signs, delta G is always going to be positive and non-spontaneous. The other two, it depends on the temperature. So if we have positive and positive, the reaction will be spontaneous at higher temperatures. What do I mean? Because positive delta H is not favorable, but positive delta S is. So there's a conflict. So it's going to be when T delta S is greater than delta H, it'll be spontaneous. Right? So it's when T delta S which will be negative in this case, is larger than the positive delta H, then you'll have a spontaneous system. And again, if they're both negative, it's the opposite. It'll be spontaneous at lower temperatures. When T delta S is lower or smaller than delta H. So that's how this works. You have to think about the signs. So this square kind of helps. Well, let's try to apply this information now. So pause it if you need to write that down. Otherwise, let's look at another problem. Say we're looking at this reaction. Gaseous sulfur hexafluoride going to liquid sulfur hexafluoride. When would that reaction be spontaneous? Go ahead and pause it if you need to. Otherwise, I'll get into the answer. All right, again, it's going to be spontaneous at low temperatures. Right? We're going from a gas to a liquid. Gas to liquid means that it has a, right, what's going on here? What's the sign of delta H? Gas to liquid, as you're going that direction, it's going to be exothermic. Delta S, gas to liquid is a decrease, so that's negative. So they're both negative, and when they're both negative, again, looking back here, both negative, they're going to be spontaneous at lower temperatures, which is true. As you go to higher temperatures, you tend to go towards the gas. As you go to lower temperatures, you start to head back towards liquid. All right. Few notes about this delta G. We are often going to write this delta G with a degree sign there. Okay, and that degree sign means we're at standard conditions. So when we have the delta G with the degree sign, And again, often we'll just write it as delta G degree is equal to delta H minus T delta S. The degree sign means you're at standard conditions. Standard conditions means that you are at a concentration of 1 molar, if it's a molarity, or if it's a partial pressure, the partial pressure is 1 atmosphere. So it's very important. Standard conditions refers to the concentrations, and the concentration will be 1. And then that'll be the standard free energy. And we'll see later on how you deal with non-standard versus standard. All right, so let's talk about the standard free energy. For a gas, again, the standard states have a partial pressure of 1 atmosphere. For a liquid or solid, it's just a pure substance. And then for a substance in solution, a concentration of 1 molar. So we have a standard delta G. We also have a standard delta S, the standard entropy. Notice here, these are not deltas. These are absolute values. How is it that we've always been delta this, delta that. So now we don't have a delta in front of the entropy of the products minus reactants. Again, a lot of these calculations, they're state functions, just like the thermochemistry chapter last year. So it's often just looking at products minus reactants. So why is it that we don't have the delta there? Because those standard molar entropies are absolute values. There is a 0 value for entropy that we can compare things to. And this is based on what's called the third law of thermodynamics. And the third law of thermodynamics states that the entropy of a perfect crystal at absolute 0 is 0. And so when you look at these absolute entropies, you're going to find this in the appendix to your book. You'll also find delta H, standard delta H's, and standard delta G's. You'll need these in the calculations. So they won't give you the absolute entropies. They won't give you the standard free energies or standard enthalpies. Those will be in the appendix to your book. So you want to make sure you can find those for the homework problems. We'll give them to you, of course, on the test. So again, why is the entropy 0? Okay, a perfect crystal, every atom only has one place it can be in. And so if there's only one microstate, remember the definition of entropy is S is equal to K ln of W. If W equals 1, then ln of 1 equals 0, so then S equals 0. All right. How do we do calculations with this? And we're getting kind of close to the end, but the way we do these calculations is like the thermochemistry chapter, that we can calculate the entropy change in a reaction. The entropy change in a reaction is equal to the sum of the entropies of the products minus the reactants. So it's just a difference in entropy between the products and reactants. You do have to take into account the stoichiometric coefficients. So if you have 2 waters, you need to multiply by 2 times the entropy that you get from the back of the book in the appendix. And the state of matter is important, right? So for water, you could have solid, liquid, or gas. Each of those have different values of the entropy. So you need to use the correct state and then multiply by the stoichiometric coefficient. So the last thing we'll do today is to do a few of these examples. First, let's predict the signs for a few of these. So I'll give you a few minutes. Predict what sign. Now, we're not doing the calculation. You should always just, before you do the calculation, predict what the sign of this is going to be. So for these 2 reactions, what will the sign be for delta S? So go ahead and pause it, and once you get an answer, turn it back on. All right, so hopefully, let's see, you got these right. So what do we have going on here? There should be a decrease in entropy. There should be a negative delta S for this one. Why? There's 1, 2, 3 moles of gas on this side, and there's a solid. Solids have low entropy, so there's only 2 moles of gas. So we're reducing the number of moles of gas in the reaction. That's going to be a decrease in entropy. All right, what about the second one? We go from 2 moles of gas over here to 1, 2, 3 moles of gas. So it's an increase in entropy because there's more moles of gas on the product side, so delta S would be positive. All right, because one of the simplest mistakes you can make on the actual calculations is to not, to get the sign wrong. So if you could predict what the sign will be ahead of time, you can catch that type of error. All right, so let's look at actually the calculations. Here's that first reaction. Now, I just went and scanned a few pages from the appendix. You can see in the appendix that we have the substances, you got all the different substances that have iodine or iron or nitrogen on the other side, or oxygen or sulfur, has a bunch of different compounds underneath it. We have the delta H is the first column. This is your standard delta H of formation, if you remember that. Your standard delta G of formation, if you remember what the formation reaction is, that's the reaction for the formation of 1 mole of that product from the elements in their standard states. We'll talk more about that on Wednesday. And this is your absolute entropy. So this third column is what we're looking at. And I had to go grab one for hydrogen. But notice, right, if we have water, here's water as a liquid and a gas, right? You want water, you don't want H2O2. O2, O3. So you have to get the right molecule in the right state of matter. Oh, here we have a hydrogen sulfide as a gas or aqueous. So make sure you get the right molecule with the right formula, right, and the right state of matter. And then we have to go grab these. So I'm going to go grab the standard entropies for hydrogen sulfide, for sulfur dioxide, for sulfur. Sulfur is the rhombic. That's the standard state. So that's why it says rhombic there. Don't need to memorize that. We'll give you the values that you need. And then water as a gas. All right, here we're going to set this up. I'll just grab those numbers from the table. So here's my values of the entropies. So for hydrogen sulfide, it was 205.8. Sulfur dioxide was 248.2. Sulfur was 32.1. And this was 188.8. And these are joules per mole.Kelvin. One thing about these numbers, notice that if you remember, like sulfur, the delta H of formation for an element in its standard state is equal to 0. So you can see this is the standard state of sulfur. The delta H and the delta G are 0. But the entropies are not 0. So even for things like here with sulfur, or here with iron, or here with O2, just because something has a 0 for delta G of formation or delta H of formation, the entropies are not going to be 0. All right, so we have all those values. How do we do this? Remember, the equation is that the entropy change for the reaction is equal to the sum of the number, you got to take into account the number of moles of each thing times its absolute entropy for the products, minus the sum, its number of moles of the reactant times its absolute entropy. All right, so let's just start plugging in the values. The entropy change for this reaction is equal to, all right, we have sulfur, right? It's going to be 3 times the absolute entropy of sulfur plus 2 times the absolute entropy of water. Again, it's water as a gas. Minus 2 times the absolute entropy of hydrogen sulfide minus the absolute entropy of sulfur dioxide. Some people, you could do sulfur plus water minus, and then in parentheses, the hydrogen sulfide plus the sulfur dioxide. I like to do minus minus for the reactants just to avoid having to change the sign later. Then we just plug in the numbers for each of these. 3 times 32.1 plus 2 times 188.8 minus 2 times 205.8 minus 248.2, and you just plug this into your calculator. You should have an entropy change for this of minus 185.9 joules per Kelvin. All right. That's your answer. All right, let's do one more. Here's that second reaction. Go ahead and calculate that entropy change. And while you're working on that, you can pause this. We'll post the answer. The answer, if you pause it, if you are still working on it, but you should come back, right? And your answer here should be, we said it would be what sign? Right? You should get 188. But is it positive or negative? We're going to go with positive because you're increasing the moles of gas. All right, so that's it for today. If you have any questions, talk about those on Wednesday. Otherwise, remember there's a quiz tomorrow. So make sure you're ready for that, and I will see you then.